Why does anything in the universe have mass at all? Your body, the air you breathe, the stars above, you might assume mass is an obvious property. Yet for decades, physicists faced a deep puzzle. Their best theories predicted that many particles should be massless. So why are they not? The answer, it turns out, lies in an invisible field filling the cosmos, one we cannot see but that changes everything. Stick with me, and you will see mass in a completely new light, emerging from a field whose quiet background value makes matter possible. And that puzzle begins with light itself. Hey everyone, thanks for tuning in. Before we begin, just a quick housekeeping note. If you enjoy what I'm doing, a like and subscribe would be really helpful. It goes a long way in keeping the channel going. And don't forget to drop a comment. I'd really love to know what you think. The puzzle of mass started with a contradiction at the core of physics. On one side, the universe contains particles that move effortlessly, like photons, which have no rest mass. On the other hand, it contains undeniably heavy particles, anchoring the world of matter you see. Why should nature assign mass so unevenly when the same fundamental rules were meant to apply to all particles? The Standard Model was meant to explain. It provided an exquisite account of how particles and forces are connected, unified by a principle called gauge invariance. In simple terms, gauge invariance means that specific hidden shifts in the equations leave the physics unchanged, much like how adjusting the electric potential in a circuit doesn't change the magnetic field it creates. These symmetries were crucial for consistency, but they came with a cost. When physicists applied them to the weak nuclear force, the mathematics predicted that its force carriers, the W and Z bosons, had to be massless, just like the photon. On paper, that seemed fine. But experiments told a very different story. Detectors revealed that the W and Z bosons were not only massive, but far heavier than a proton itself. This stark conflict between symmetry and measurement was not a minor mistake. It struck directly at the foundations of the Standard Model. Theory insisted on massless bosons, while nature insisted otherwise. Something fundamental was missing. That missing element was essential. Without mass for the W and Z bosons, the weak force would act over infinite distances instead of being limited to a tiny range. And without mass for electrons, atoms could not attach to nuclei. Chemistry, biology, and even stars would never come into existence. Most of the mass of protons and neutrons does not come from the Higgs field itself, but from the energy that holds quarks together through the strong force. However, without the Higgs mechanism giving quarks their masses initially, and without stable electrons orbiting protons, the fundamental components of ordinary matter could never form something stable. The issue of mass lies at the core of why the universe appears as it does. The problem was not just practical, it was mathematical. If you tried to add mass directly into the equations, the delicate balance that ensured accurate calculations would break down. This was because inserting a mass term manually would violate gauge invariance, thereby losing the ability to make controlled predictions. Physicists refer to those dependable predictions as renormalizable, meaning that infinite values do not flood in to corrupt the mathematics. Without that safeguard, the entire theory would collapse. Hence, the deadlock deepened. W and Z bosons existed, heavy and real, but the equations could not accommodate their mass, without destabilizing themselves. It was like trying to fit an oversized piece into a puzzle that clearly disallowed it. Something had to give. But what? The breakthrough insight was that perhaps particles did not carry their mass from the start. Instead, maybe they acquired it through interactions with an unseen field that is spread throughout the universe. If such a field had a non-zero value even in space, a background presence known as a vacuum expectation value, it could transform initially massless particles into massive ones. Interaction terms in the equations, which are harmless under gauge symmetry, would effectively act like mass terms once this hidden background is taken into account. This approach preserved the beauty of symmetry in the equations while allowing mass to exist in reality. W and Z bosons gained their weight without violating the rules. Quarks and charged leptons gained the masses that enabled protons, neutrons, and electrons to form atoms. The mechanism did not involve friction or resistance. Nothing slows particles down in a viscous medium. Instead, their very identities in relation to the field assigned them mass as a built-in property. That idea redefined what it even means to be heavy. A particle is not burdened because it drags through a cosmic fluid. It is heavy because of its strong coupling to this hidden field. Those couplings vary from particle to particle, which explains why the spectrum of masses is so diverse, from swift neutrinos to hefty bosons. Suddenly, the jagged landscape of particle masses was not arbitrary, but a reflection of a deeper order. Still, the proposal was unsettling. No one could identify a spark, a compass swing, or any direct evidence of this mysterious field. It was present everywhere, yet invisible. It had to operate uniformly throughout space, offering no clear means by which it could be detected by ordinary means. That invisibility left many skeptical. But the paradox it solved was significant, and the mathematical consistency it maintained was alluring. The field seemed less like an optional decoration and more like a necessity. For decades, theorists examined this balancing act. The Standard Model could describe particle interactions beautifully, matching experiment after experiment. But this gap grew larger with every new result. Each confirmed mass strengthened the case that an unseen process endowed particles with weight. The deadlock became evident. Without a mechanism to reconcile gauge invariance with massive particles, the Standard Model risked collapsing. By the early 1960s, the stalemate had firmly established itself. Symmetry demanded one reality. Experiment revealed another. Physicists searched for ways to reconcile the two without compromising the elegance of their equations. The idea started to develop that symmetry itself might not be explicitly broken, but instead concealed from view, hidden within the vacuum that underpins all of nature. This was a daring idea, that the vacuum itself could influence the masses of particles. In a remarkably short time, several groups of theorists arrived at a similar solution. They argued that what seemed to be conflicting demands between symmetry and mass were not actually conflicts, but signals of a deeper mechanism at work. If correct, it explained not only why the W and Z bosons were massive, but also why the universe contained stable matter at all. It was a new way to imagine the very ground state of reality. That idea was nothing less than revolutionary. It introduced the concept of a universal field with a constant background value permeating space, along with the possibility of a new particle, a quantum excitation of that field, awaiting discovery. Finally, physicists had a way to reconcile both pillars: the power of gauge invariance in the equations and the clear experimental evidence of heavy force carriers. But in the 1960s, all of this remained theory. An elegant idea on paper doesn't make it accurate. To embrace it required extraordinary confidence, because no laboratory had ever glimpsed such a field, let alone the particle it suggested. Yet, these ideas would come to reshape the field of physics. What started as a stubborn puzzle had transformed into a new framework for understanding mass itself. And remarkably, it was not the result of a single flash of inspiration, but of several minds converging on the same conclusion. Different teams, working independently, each arrived at similar answers. That convergence was the next twist in the story, and it changed the course of particle physics forever. In 1964, 6 physicists conceived an idea that would revolutionize our understanding of matter itself. François Englert, Robert Brute, Peter Higgs, Gerald Guralnick, Carl Hagen, and Tom Kibble worked in 3 separate groups in different locations without knowing what the others were doing. Each pursued their own reasoning to its logical conclusion. When their papers appeared, the solutions were remarkably similar. This convergence suggested that they had not stumbled upon a mere mathematical curiosity, but had discovered something more fundamental: patterns in the equations that indicated a hidden order in nature. At the heart of their approach was a bold concept: spontaneous symmetry breaking. To understand this, you need to consider what symmetry means in physics. Symmetry here does not refer to visual beauty, but to rules that hold regardless of how you shift or rotate a system. Gauge symmetry, the principle guiding the standard model, required certain force-carrying particles to be massless to preserve the theory's consistency. Yet experiments demonstrated otherwise. W and Z bosons clearly possessed mass. How could both the demands of symmetry and empirical evidence be reconciled? The idea of breaking symmetry offered a potential solution. Imagine a ball perfectly balanced on the top of a circular ridge. At that exact moment, the setup is symmetric. All directions appear identical, with no side favored. However, sustaining such a balance is practically impossible. A tiny, even invisible disturbance will cause the ball to roll down, selecting one direction from many. The laws that maintain the circular ridge stay unchanged, but the actual outcome, the ball resting in one valley, constitutes a break in symmetry. This explains what spontaneous symmetry breaking means. The rules of the system still respect symmetry, but nature selects a stable configuration that does not. In the universe, this meant that the underlying fields did not stay balanced on a ridge. Instead, they settled into a specific arrangement, a vacuum state that led to unexpected consequences. These consequences were exactly what was needed. Particles predicted to be massless could now acquire mass through their interaction with this new background state. The mechanism worked elegantly. The modes that would have appeared as separate massless particles, called Goldstone bosons, did not emerge on their own. Instead, they were absorbed into the W and Z bosons, becoming their longitudinal components. It was this absorption that gave the gauge bosons mass. Nothing in the mathematics was broken. The symmetries of the theory remained quietly beneath the surface, even as the physical world appeared only in its broken state. This clever exchange resolved the deadlock. Gauge symmetry was preserved in the underlying equations, so the standard model remained mathematically consistent. Yet, thanks to symmetry breaking, the W and Z could now carry mass, perfectly matching experimental observations. Both the elegance of theory and the evidence of reality had been maintained. The ridge and ball illustration remains useful. If you could reset the ball to the top, the system's circular symmetry would become clear once again. The laws still maintain that symmetry, but the ball stays fixed in one valley, which represents the reality of our universe's vacuum. What appears symmetric in theory often proves to be broken in practice. This leap of thought allowed physicists to understand mass without disrupting harmony in their equations. From this reasoning came a striking prediction. If a field fills the universe, enforcing this symmetry breaking, then ripples in that field must exist. In quantum terms, that ripple is a particle. The Higgs boson was not an extra piece added for convenience. It was the inevitable quantum excitation of the Higgs field, a requirement of the mechanism itself. Without such a particle, the structure of the argument would collapse. The fact that 6 different researchers independently arrived at the same conclusion added strength to the idea. Each had started from a different angle, yet all arrived at the same valley. Such convergence is rare in science, and it often suggests that the mathematics was not forcing them to invent tricks, but guiding them toward truths woven into nature's fabric. Even without experimental proof, the proposal carried an air of necessity. Still, despite its elegance, this remained purely theoretical. Equations alone could not make the Higgs field visible to humans, nor could the Higgs boson be pulled from the shelves of laboratory equipment. The proposals painted a consistent picture of why matter has mass, but none provided immediate physical evidence. Broken symmetry looked impressive on paper, but without proof, it stayed a conjecture. The Higgs particle existed only in the realm of theory. This lack of evidence created tension. A field that fills the universe, invisible yet giving substance to everything, explained much. However, it demanded belief without confirmation. For a generation of scientists, the idea was only a quiet conviction, too elegant to dismiss, too significant to ignore, yet still without a single verified sign in experiments. 6 researchers in 1964 had proposed a way out of the paradox, a means for symmetry to endure and particles to carry mass, with the Higgs boson theoretically waiting as the messenger of that hidden field. It was a crucial and necessary step forward, but the theory alone could not demonstrate how such a field truly functions, nor how it managed to give you, and every atom around you, its weight. That question, how something invisible could underpin your existence, remained unanswered. The invisible field resides at the core of the puzzle. Known as the Higgs field, it is not a distant or occasional influence. It does not activate in certain areas or disappear in others. Instead, it permeates the entire universe. Every point in space bears its quiet presence. Quarks within protons, electrons in their orbits, even the W and Z bosons themselves, exist solely through interactions with this ever-present background. Unlike forces such as magnetism or gravity that can be shielded or negated under special conditions, the Higgs field cannot be screened out. It is a permanent feature of today's universe. To understand why, consider its unusual energy landscape. The Higgs field does not follow the simple pattern of relaxing to zero when left undisturbed. Instead, its potential takes on what physicists often describe as a sombrero shape, with a raised peak at the center and a ring-shaped valley surrounding it. The key point is that the lowest energy state is not at the central peak, but instead on the surrounding ring. This means the natural resting value of the field, the vacuum expectation value, is not zero. Even in what we call space, the Higgs field stabilizes at a finite strength about 246 giga-electron volts. This persistent background value is why particles can couple to the field and gain mass. Imagine a flat plane with a shallow ridge in the middle and a circular valley beyond. Roll a marble onto the ridge, and it cannot stay balanced. It inevitably settles somewhere along the valley. The hill and valley are symmetrical in layout, but the marble's resting place indicates a preferred direction. Similarly, the Higgs field has a built-in minimum that is not zero, and the universe has selected that state. The field is never absent. It quietly sustains its value everywhere, forming the backdrop against which matter exists. What does this mean for particles? Each particle couples differently to the Higgs field. These couplings determine how much rest mass a particle acquires. If a particle couples strongly, like the W and Z bosons, its effective mass is significant. If the coupling is very weak, as with neutrinos, the mass is tiny. Some particles, such as photons, do not couple at all. They remain entirely insensitive to the field, which is why light is massless and travels at the universe's maximum speed. In this picture, mass is not a fixed innate property, but rather it emerges from this coupling. This is not a form of resistance or drag. The Higgs field does not push back on moving particles or sap their energy. Instead, the interaction establishes a particle's rest mass, the inherent inertia you measure if you try to accelerate it from rest. The mass is always present. It does not appear or disappear as the particle moves. It is not frictional. Nothing is lost in motion. This highlights why this mechanism is elegant, not cumbersome. The implications are remarkable. For example, the electron gains its small but essential mass through coupling to the Higgs field. Without that mass, electrons would not orbit nuclei in stable shells. Quarks, too, gain intrinsic masses via their Higgs couplings. Together, electrons and quarks enable the existence of atoms. However, over 90% of the mass inside protons and neutrons does not originate directly from the Higgs field. Instead, it arises from the binding energy of quarks and gluons interacting through the strong nuclear force, a phenomenon explained by quantum chromodynamics. Crucially, even this binding energy depends on having massive quarks initially. If quarks were massless, matter would never organize into the stable baryons and atoms we depend on. The Higgs field's role is not to provide the majority of the weight you feel on a scale, but to supply the essential ingredients that make matter exist in familiar, structured form. This redefines our idea of heaviness. Take photons. They glide through the Higgs field without interaction, remaining massless. Compare that with the hefty W and Z bosons, which couple strongly and weigh more than an entire proton. Even electrons, tiny though they are, owe their existence to the same principle. Mass is not fixed into particles at their creation. It arises from relationships with this omnipresent field. Without those connections, no stable atoms, no chemistry, and no complex structures could exist. But how can such a universal field be proven to exist? For gravity, you can observe the orbits of planets. For magnetism, you can hold a compass. The Higgs field, by contrast, simply exists, featureless and constant. No needle swings to show its value. You feel its effect every time you strike a ball or lift a book, but you cannot directly point to its presence. That made it especially elusive as a scientific idea. If you cannot see the background itself, the next step is to look for disturbances in it. Just as ripples on a pond reveal themselves when they pass, the Higgs field could show itself by producing an excitation. In quantum physics, that ripple is a particle, the Higgs boson. It is not a long-lasting wave, but a fleeting quantum vibration that soon decays into other particles. Detecting it requires tracing those decay products backwards, inferring the boson's presence indirectly. This provided the testable prediction. If the Higgs field pervades the cosmos, then the Higgs boson must exist. Confirming the boson would validate the field and confirm the mechanism behind mass. Failing to find it would challenge the standard model, dismantling the solution that explained how W and Z bosons become heavy and why atoms remain stable. The invisible field and its ripple are inseparably linked. This is where the idea gains its most tremendous significance. Your mass, which appears to be the most ordinary aspect of existence, is not just an inherent property. It indicates how particles connect to a field that cannot be switched off. Without that background, there would be no electron mass, no atomic structure, no familiar matter. Most of the mass of protons and neutrons results from strong force dynamics, but without the Higgs, none of it would assemble into the tangible objects you see and touch. So, while the Higgs field will never announce itself with a compass swing or circuit spark, it leaves a unique signature. If the background field exists, then the Higgs boson must exist as its ripple. Detecting even the faintest trace of that ghostly particle would mean uncovering the quiet backbone supporting reality. And if such a particle exists, it cannot hide forever. The so-called ghost particle was the Higgs boson. If the Higgs field extended throughout all of space, then its ripple, the boson, had to exist as well. In quantum field theory, every field is expected to have a particle that represents its quanta. Photons arise from the electromagnetic field, gluons from the strong force. For the Higgs field, the boson was its proof of reality. Detecting it would mean the background field was not just an elegant idea, but an actual component of nature. The standard model placed significant importance on this prediction. The theory had guided physics through decades of discoveries, from quarks to the W and Z bosons, each one aligning with forecasts. But the mechanism explaining why particles have mass needed its own visible sign. Without the boson, the Higgs field risked being dismissed as mere mathematical sleight of hand. That ghostly ripple was the confirmation of the entire concept of mass. It was also unusual. All other known bosons carry spin 1, behaving like vectors that respond to rotation. Fermions like quarks and electrons carry half-integer spin. The Higgs boson, by contrast, carried spin 0, making it a scalar particle. It also had even parity and no electric charge. Such a particle had never been discovered before. And unlike photons or electrons, it would be fleeting, decaying almost instantly into lighter particles. If found, it would expand the known particle family into entirely new territory. You could think of it like this. Imagine an unseen pond stretching across the universe. The pond's surface always remains calm and level. You cannot directly touch it, but you know its presence shapes everything resting above it. The Higgs boson would be like a passing ripple on that hidden surface. You never see the pond itself, only the brief quiver that proves it exists. Even the faintest ripple, caught for a moment, would confirm the entire hidden expanse. That fragile trace was crucial. Without it, elegant mathematics remained untested. Finding the Higgs boson was not just a curiosity, it was vital. One detection would turn the Higgs mechanism from speculation into fact, transforming the mass puzzle into a verified piece of physics. The boson was the witness every physicist needed to call, the one who could finally testify that the invisible field was real. But bringing this witness into the open was daunting. Unlike other particles whose properties were predicted quite precisely, the Higgs boson's own mass was left undefined by the Standard Model. The equation kept it as a free parameter. That meant no one knew its accurate energy scale. It could hide light, be easily produced, or be so heavy that no accelerator on Earth could create it. For experimenters, this was like chasing prey without knowing its size. You might prepare for a bird and find you need equipment for an elephant. This broad uncertainty explained why earlier searches faced difficulties. Each new accelerator explored higher energies and eliminated some possible ranges, gradually narrowing down where the boson might be hiding. However, exclusion was not confirmation. With each progress, the search window shrank, but the Higgs remained unseen. Year after year, detectors looked for a distinct peak amid background noise. Scientific patience was necessary. Only if a signal was strong enough to stand out from noise, meeting the gold standard of 5 sigma, indicating a minimal chance of coincidence, could physicists declare success. Anything less was merely a hint, nothing definitive. The lack of confirmation created tension. On the one hand, the Standard Model has worked remarkably well. On the other hand, its central element remained unseen. It was like watching a play where every supporting character appears on stage, but the leading actor never shows up, only discussed. As time passed, this absence grew more urgent. The Higgs boson appeared both essential and elusive. Gradually, this absence turned the Higgs into the most hunted particle in physics. Rarely had an unseen particle carried so much significance in both theory and experiment. Laboratories around the world tuned their machines, aiming to observe even a few events that could not be dismissed. The search extended beyond curiosity. Without the Higgs boson, the Standard Model's balance would collapse, leaving physicists searching for an alternative framework. The chase also added another layer of excitement. Confirming the Higgs would validate the Standard Model, but discovering any unexpected behavior, subtle deviations in how it interacted or decayed, could signal physics beyond the Standard Model, possibly linked to dark matter, unification, or the early universe's rapid inflation. The Higgs carried a double promise: to stabilize current theories while keeping open doors to new frontiers. What made the search daunting was not only its significance, but also the energy required just to attempt it. Ordinary laboratories cannot produce particles like the Higgs. To generate it, colliders had to recreate conditions similar to those seconds after the Big Bang. For a brief moment, energy densities soared enough to excite the field and produce one Higgs boson, which then decayed almost immediately into lighter particles. Detecting it involved sifting through vast amounts of debris to identify patterns in the decay. This scale of effort ushered science into a new era. The Higgs boson was no longer simply a question for mathematicians or modest instruments. It demanded colossal machines capable of colliding protons at nearly the speed of light, again and again, billions of times, to catch a few fleeting Higgs events. It required detectors comparable in size to cathedrals, engineered to capture debris and measure it with exquisite precision. It also called for collaboration on a truly global scale. What had started in 1964 as lines of algebra on a sheet of paper had now become a global quest to create instruments capable of detecting the Higgs boson. The ghost particle had drawn humanity into the most significant scientific endeavor ever undertaken, one whose sole purpose was to evoke and identify the faintest ripple of an invisible field. The search for the Higgs was not merely about spectacle. It was about closing the gap in the most successful theory of matter ever developed. With the ghost particle still elusive, the standard model remained incomplete. The urgency to find it drove increasingly daring engineering as the scientific community prepared for one of the most ambitious machines in history. And so, the story continued, with the question no longer whether the Higgs field was elegant, but whether humanity could build the tool powerful enough to reveal its ripple. That ambition soon took form in the shape of a vast ring hidden beneath the Earth. Why did humanity commit to building a 27-kilometer tunnel in pursuit of a single particle? At first glance, it sounds extreme. Most people imagine scientists at blackboards or working in small laboratories, not enormous rings buried underground. Yet, the Higgs boson could not be observed with ordinary tools. To see it, scientists had to recreate, even briefly, the immense energies present in the early moments of the universe. And that meant collisions. Only by smashing protons together at nearly the speed of light could energies reach levels where particles like the Higgs might momentarily appear. Imagine striking a crystal with a hammer. A gentle tap does nothing, but a decisive blow can reveal hidden patterns. For the Higgs, the hammer had to strike much harder than any previous accelerator had managed. Enter the Large Hadron Collider, commonly called the LHC. This underground ring spanned borders, designed as the largest scientific instrument ever built. Protons were injected into its twin pipes, then accelerated in opposite directions by strong electric fields and kept on track by ultra-cold superconducting magnets. The particles circled endlessly, gaining energy until they reached conditions similar to those a trillionth of a second after the Big Bang. When the two beams were steered into collision, the resulting energy density briefly created conditions in which rare particles, including the Higgs boson, could flicker into existence. Even then, the Higgs was far from ordinary. Out of hundreds of trillions of collisions, only a few created the right conditions for the boson to appear. And even in those cases, it existed only briefly before decaying into lighter particles, which scattered outward in showers of debris. Detecting the Higgs meant not actually seeing it directly, but reading its imprint in the wreckage. You might compare it to watching a firework display, where millions of sparks burst at once, and within that chaos, a single faint spark you seek appears once in a million tries. The task of tracking those faint traces fell to two enormous detectors, AT, LAS, and CMS. Although both were situated at points where the proton beams intersected, they were constructed differently, utilizing separate technologies and layouts. That difference was intentional. Science could not rely on a single measurement, so two independent experiments were required, each verifying the results of the other. Only if both experiments agreed would a discovery be accepted as genuine. Coupled with the strict statistical threshold of 5 sigma, the level that ensures the likelihood of being misled by random noise is extremely low. This double safeguard provided confidence in the results. Each detector functioned like a finely layered instrument, sometimes likened to a digital onion. The innermost layers traced the precise paths of particles as they shot outward. Further out, thicker layers captured the energy they carried, while outer chambers detected those particles capable of penetrating all layers. Every collision, occurring at astonishing speed, generated data. That data was then filtered and stored, the flow so vast that it required one of the largest computing systems ever constructed. Each year, the LHC computing grid processed volumes of information measured in many petabytes, gradually reducing chaos until only meaningful signatures remained. In some ways, the detectors designed to find the tiniest units of nature were among the most significant scientific structures ever built. Towering multiple stories high and packed with cables, sensors, and electronics, they exemplified the paradox of experimental physics. The most minor traces needed enormous machinery to detect. The construction of the collider required equally daring engineering. Superconducting magnets had to carry huge currents, made possible only by cooling them to ultra-low temperatures where electrical resistance vanished. The vacuum inside the beam pipes had to be cleaner than interplanetary space to prevent stray atoms from deflecting the beams. Timing systems had to synchronize millions of components so that two proton beams, moving almost at the speed of light, could be steered into collision at precisely the right places and times. These were not science fiction fantasies. They were real solutions designed solely to help humanity uncover a single hidden particle. Stepping back from the blueprints and figures, the scale is remarkable. A problem that began as a mathematical contradiction in 1964 had grown over decades into the construction of not just a tunnel, but an entire machine spanning nations. Thousands of scientists, engineers, and students pooled their knowledge to bring it to life. This was not the effort of one institution or country alone, but a collaborative venture across the globe, more akin to a cathedral of magnets and data than a conventional laboratory. What makes this story even more compelling is how delicate the target was. The Higgs was nicknamed the most wanted particle, not to exaggerate, but because no other theoretical prediction had demanded such an effort. Decades of theory had given confidence that it must exist, yet not a single glimpse had confirmed it. Entire generations of researchers lived and worked in its shadow, knowing their machines had to be precise enough to distinguish an extraordinary whisper from the roar of background noise. And so the collider operated year after year, with the two great detectors collecting and filtering the flood of events. The computing grids processed the influx of information into identifiable patterns. Gradually, hints began to emerge. Small excesses at specific energies, tiny bumps above background expectations. Most such signals proved fleeting, fading as more data was gathered. That is the nature of experimental physics. Only when a signal remains strong and both ATLAS and CMS observe it independently does excitement start to shift towards certainty. Eventually, the signs aligned. Both detectors started to see apparent excesses at the same energy level. The pattern persisted as additional data was collected, surviving every test of skepticism. The results exceeded the 5 sigma standard. What was once mere speculation now carried the weight of evidence. That moment changed modern physics. In one stroke, the existence of the Higgs boson confirmed decades of theory, validated the Higgs field, and secured the mechanism that transformed massless equations into the material world you experience. And just as remarkable, the achievement demonstrated that humanity had not only built the largest machine on Earth, but also a machine that fulfilled its precise purpose. Even today, the LHC continues. Measurements are refined, questions remain unanswered. Researchers investigate whether the Higgs particle adheres to every expectation of the standard model, or whether it reveals cracks that could lead to new insights. Yet one truth remains unshaken. The collider succeeded in detecting the subtle signature of the ghost particle. What followed was a moment when science stood still, waiting for words that would rewrite the story of matter itself. On the morning of the 4th of July 2012, the scientific community's focus shifted to Geneva. For decades, the Higgs boson remained a theoretical possibility, a predicted particle that theory anticipated, but that experiments had yet to confirm. Now, The two major detectors at the Large Hadron Collider, ATLAS and CMS, were prepared to present their findings. Thousands had eagerly awaited this moment. The future of half a century's worth of ideas about mass depended on what would be revealed. Both collaborations presented evidence for a new boson. Each detector operated independently, employing different architectures and approaches, yet both pointed to the same result: an excess of events at approximately 125 giga-electron-volts. This was not a mere suggestion, but a signal that satisfied the rigorous 5 sigma standard. In collider physics, this level of certainty signifies overwhelming confidence that the result is genuine, not a statistical anomaly. Two separate experiments had converged on the same mass range and the same high level of certainty. To those unfamiliar with the field, 125 giga-electron-volts might seem arbitrary. However, for physicists, it precisely aligned with long-standing calculations and exclusions. Earlier experiments had ruled out heavier masses. Lighter ones did not conform to the delicate balance of the standard model. Within this range, at last, the theory and the particle accelerator data intersected. The Higgs boson was not merely a possibility, but was expected to appear here, and the data confirmed its existence. The implications were immediate. For years, the Higgs field was a hypothetical necessity, the quiet scaffold that explained why W and Z bosons were heavy, while photons were massless, and why quarks and leptons had inertia. However, without its partner particle, the field could have easily been dismissed as unprovable. With the boson confirmed, speculation hardened into fact. The mechanism first outlined in 1964 was validated. Symmetry breaking, the non-zero vacuum field, the sudden appearance of rest mass, all of it was supported by observable evidence. The human reaction showed the magnitude of the achievement. In auditoriums and control rooms, veterans who had dedicated their careers to the search saw the curves appear on screens. Peaks around 125 giga-electron-volts, rising clearly above the expected noise. Younger scientists who had joined the field just as the LHC was being built watched a result that proved why the collider had been constructed. Some responded with cheers, others with quiet tears, recognizing that a journey started decades earlier had now reached its goal. It is worth pausing to consider the scale of what has been achieved. A particle that decays in less than a trillionth of a second requires thousands of people working across continents to be observed. Quarks and leptons, which gained their identity through the Higgs, in turn gave rise to planets, life, and everything we see. Yet the essential proof of their underlying story existed as a fleeting excess on a graph. That is why the day carried significance beyond physics. It symbolized how perseverance and international collaboration can uncover truths beyond imagination. The contrast with 1964 could not have been more apparent. That year, 6 theorists published bold equations proposing a hidden field and its associated boson. At the time, they admitted it might never be testable. In the decades that followed, the framework was accepted, albeit as an incomplete model, because its hallmark particle remained unobserved. Then, in 2012, the prediction shifted from abstraction to evidence. What had once been a ghost in mathematics now had a measured mass. For many in the room, it was like hearing an echo that had finally been answered. The immediate result was a cultural shift in the field of physics. Textbooks that had contained caveats in their chapters were rewritten. Students now learned that the Higgs boson was not a speculative placeholder, but an actual part of the particle family, confirmed as firmly as the electron or the photon. The standard model, which had been considered incomplete for decades, was now understood in its essentials. A missing piece had been put into place, and the structure remained whole. Recognition at the highest level came soon after. In 2013, the Nobel Prize in Physics was awarded to François Englert and Peter Higgs for the theoretical insight that had introduced the mechanism nearly 50 years earlier. Thousands of others had made the experimental confirmation possible, and their work remained vital. However, the prize recorded in history was that the original idea had been validated by nature itself. The Higgs boson had moved from speculation to discovery, and the world acknowledged its importance. The scene remains one of the most striking examples of how human patience and technology come together. The Standard Model had predicted its missing element. Experiments had gradually edged closer each year, ruling out possible hiding spots and narrowing the range. Then, one morning, a clear result emerged, and the multi-decade question was answered with a few definitive plots. Few events in science evoke such unity between thought and reality. Meanwhile, the wider world responded with a mix of fascination and sensationalism. Popular headlines dubbed it the God particle, a term that captured the imagination but obscured its meaning. Physicists preferred to speak more plainly. A new boson had been detected, consistent with the Higgs, and the data confirmed the mechanism that gives particles mass. Beneath every headline, the fact remained solid. The Higgs field existed, and its ripple had been observed. This is where the story takes its next step. With the Higgs boson confirmed, the main question about mass had an answer. But you might wonder what difference this makes to you, or what new questions it raises. Because in physics, discovery rarely closes every door. It often opens new ones, pointing to puzzles just as profound. So, what did the Higgs boson actually reveal when it was discovered? At first, it might seem like the confirmation of just one more particle, distant from everyday life. However, its significance lies in the fact that it explains why matter has mass at all. The Higgs boson was the ripple that proved the Higgs field is real, and that field is the quiet foundation that allows particles to carry mass while keeping the mathematics of physics consistent. The main achievement is this: the Higgs field resolved how particles can have mass without breaking gauge invariance, the key symmetry that holds the Standard Model together. Simply inserting masses into the equations would have broken that symmetry and disrupted calculations. But because the Higgs field maintains a non-zero value everywhere in space, it naturally transforms specific interaction terms into mass terms. This mechanism maintained the theory's consistency while assigning particles the mass they are observed to have. When the boson was discovered, it confirmed that this was not just convenient algebra, but a genuine feature of nature. Consider what that means. Without the Higgs field, the carriers of the weak force, the W and Z bosons, would be massless, and the weak interaction would extend across the universe instead of being confined. Electrons would be weightless, unable to orbit nuclei. Atoms could never form, and chemistry would come to a halt before it even began. A universe without mass from the Higgs would be a universe devoid of stars, stable matter, and life. It is also worth noting that most of the weight you personally feel on Earth doesn't come directly from the Higgs itself. The protons and neutrons that make up nearly all the mass of everyday matter derive most of their heft from the energy of quarks bound together by the strong nuclear force, the complexity of quantum chromodynamics. However, this binding energy only exists if quarks have masses to begin with. and those masses originate from the Higgs field. The Higgs also provides electrons with their tiny but vital mass, which allows atoms to exist in the first place. In summary, the Higgs does not account for every gram of matter, but without it, none of those grams could ever have come together. When experimentalists studied the Higgs boson after its discovery, many were surprised by how precisely its behavior aligned with theory. The boson decayed into pairs of W or Z bosons, into two photons, and into fermions such as bottom quarks and tau leptons, all at rates predicted by the Standard Model. The accuracy of these matches was remarkable. Each decay channel served as a separate test of the theory, and all of them concurred with the results. Such precision reassured physicists that the mechanism proposed decades earlier was not only ingenious, but also accurate. Imagine a machine made of beams and joints, with one vital screw missing in the middle. Without it, the entire framework wobbles under stress. You suspect the screw exists, but cannot verify it. One day, you find the screw exactly where the building plan indicated, and it fits perfectly. Instantly, the structure stabilizes. The Higgs boson was that missing fastener. Once in place, the Standard Model no longer wavered under the weight of experimental evidence. This redefines what it means to have mass. Mass is not something particles possess in isolation. It arises from their relationship to an underlying field. Quarks and leptons interact with the Higgs field, and thus they acquire identity. Photons do not couple to it, so they remain massless. The W and Z bosons couple strongly, which is why they are heavy. Even the Higgs itself is a fleeting manifestation of the field into something measurable. Your own body owes its solidity not just to mass, but to the steady, persistent presence of this universal backdrop. That discovery brought immense relief to physicists. For decades, the Standard Model had succeeded brilliantly, but always without the Higgs particle. Without it, the framework was incomplete, elegant, yet lacking a full explanation. With its discovery, that gap was filled. Now textbooks can confidently state that this is how the weak bosons and matter particles gain their mass. The Standard Model, including the Higgs, remains the most successful description of the particle universe achieved so far. Yet even as celebrations echoed, new questions emerged. The Higgs does not explain gravity, the dominant force governing planetary systems and galaxies. It does not account for dark matter, the unseen material that outweighs visible matter many times over. Nor does it address dark energy, the unknown force driving the universe's accelerated expansion. And it does not explain why the early universe expanded so rapidly immediately after the Big Bang. The Higgs solved one of science's major problems, but left others unresolved. In this sense, the discovery is both an ending and a new beginning. It completed the Standard Model, but it also provided researchers with a new tool for exploration. Because the Higgs behaves so precisely as predicted, any slight deviation in its measured properties could reveal entirely new physics. Scientists now examine its properties with great care. One important open question is whether the Higgs boson couples to itself as the theory predicts. Measuring that self-coupling involves observing Higgs bosons appearing in pairs, a process that is extremely rare but highly revealing. These are the kinds of probes that might one day show flaws in today's understanding. The revelation that mass is a result of interaction rather than an inherent attribute of each particle also changes how you perceive matter's identity. Protons, neutrons, and electrons seem solid and definite, with masses listed in tables. Yet those values are not fixed. They depend on the existence of the Higgs field and its constant background value. Without it, the very concept of stable particles would fall apart. In that sense, the Higgs exposed the dependency built into everything you touch. Look further out and the scale expands. The Higgs field explains why matter retains its shape, but it leaves unanswered the broader structure of the cosmos. How does gravity integrate with quantum theory? What causes dark energy? Why is the Higgs mass what it is? These questions hang over the completed Standard Model like unfinished chapters waiting to be explored. That is why the day of its confirmation brought as much restlessness as relief. Solving the problem of mass only heightened curiosity about everything beyond it. Already, researchers have begun to wonder whether the Higgs mass itself conceals clues. Could it relate to hidden forces connecting known particles to dark matter? Could it be linked to the energy scale of inflation that once stretched the young universe? The more firmly the Higgs was established, the more urgent those surrounding mysteries seemed. For you, the Higgs boson offers two interconnected insights. First, it confirmed the story of how particles acquire mass and why the physical world remains stable. Second, it demonstrated that physics still extends far beyond what we currently understand. Having observed the field, the next step is to test it, probe it, and see whether it hints at new physics that extends beyond the Standard Model. And here lies one of the deepest connections between this discovery and the broader fate of everything. The Higgs boson does not merely explain why atoms exist today. Its measured value may also suggest the ultimate stability of the universe itself, raising unsettling questions about how secure reality remains in the long run. The Higgs boson also carries an unexpected implication. It raises the question of whether the vacuum that forms the foundation of physics is entirely stable or only barely so. The figure measured at the collider, around 125 gigaelectron-volts, may seem ordinary at first glance. However, when compared to the mass of the top quark, the heaviest known particle, the two values together suggest that our universe might be near the boundary between stability and fragility. The state of reality might not be the deepest possible resting point, but a temporary one. To understand why, you need to consider the Higgs potential, the shape of the energy related to the field. Generally, the actual vacuum of the universe should correspond to the lowest possible energy. If the field resides there, it is stable. No further change can occur without external influence. But if the field's current position is only a local minimum, with a deeper valley hidden beyond, then the vacuum is metastable. This means it appears stable on the surface, but could, in theory, shift through quantum tunneling into a lower state. Imagine a village built at the bottom of a valley. To its inhabitants, the valley floor is the lowest point they know. Life there feels secure. Yet beyond distant mountains lies an even deeper hollow, unseen. The villagers never move, and on standard timescales, nothing changes. However, geologically, it is possible that the land could one day give way, sliding into the lower ground. For the universe, a similar possibility exists. The Higgs value might not rest in the deepest basin, but on a ledge above another. Here, the top quark has a special role. Its large mass strongly interacts with the Higgs field, influencing the potential in different ways depending on the exact value. If the top quark were lighter, the vacuum would appear comfortably stable. If heavier, it might already be tipping towards instability. Current measurements place us right at the edge between the two states. Neither side is confirmed. We exist in that precarious middle ground. It is important to emphasize what this signifies and what it does not. Over the span of human history, planetary evolution, or even the lifespan of stars, there is no immediate danger. If our vacuum truly is metastable, its predicted lifespan is unimaginably long, many billions of years beyond the current age of the universe. Thus, this is not a forecast of imminent change, but a statement about the mathematical framework of our universe. The fact that such fragility appears in the equations is what makes it remarkable. Another striking feature is that the numbers do not clearly place us within one category or the other, but along a knife edge. The Higgs mass, along with the current estimate of the top quark, conspires to position the universe between complete safety and a potentially temporary state. If the Higgs boson had been slightly heavier, or the top quark a little lighter, the vacuum would seem permanently safe. Conversely, if they had shifted the other way, instability would already dominate the equations. Instead, we find ourselves balanced between these extremes. This prompts reflection on fragility. You observe rocks, continents, and planets, assuming their permanence. You interpret physical laws like Newton's and Maxwell's as absolute certainties. However, the vacuum that underpins those laws may not be entirely absolute itself. Beneath the illusion of permanence, there may be something that prefers a different state, hidden yet theoretically possible. The discovery of the Higgs boson, rather than ending the story on mass, suggests that even the fundamental basis of existence might not be as fixed as we assume. For physics, this tension becomes a catalyst. If the Higgs mass indicates metastability, the standard model cannot be complete. Something else must fill in the gaps. It could be undiscovered symmetries supporting the vacuum against collapse, hidden particles shifting the balance, or perhaps other Higgs-like fields quietly reshaping the landscape we inhabit. In any case, the boson transforms from merely giving mass to being a messenger that raises more questions. This is why ongoing precision remains essential. The fate of the vacuum hinges critically on the numbers. A change of less than 1% in the top quark's mass, for example, could redefine the verdict from metastable to stable. Physicists analyze each detail carefully. Every new run and detector upgrade that refines these measurements sharpens the overall picture. It is not about sensationalism, but about gradually honing our understanding. Along the way, the Higgs has evolved from a discovery to a probe, an opening to questions that extend beyond current theories. The effect is humbling. You might hope the Higgs resolved all loose ends neatly. Instead, it emphasized how dependent the universe is, a delicate balance on precise values that could have been different. There is no sign of immediate danger, and the timescales far exceed even the lifespan of galaxies. Yet, the lingering feeling remains that reality is based on values that just barely hold together. The Higgs turned out not to be the end of a sentence, but punctuation that alters how you read the entire paragraph. So, the core message is not about doom, but about perspective. It suggests that the world around you, no matter how solid it appears, relies on finely tuned conditions at the quantum level. The stability we often assume may not be absolute, but conditional, perhaps guaranteed by fields and forces we have yet to observe. The boson, celebrated as the answer to why matter has mass, now serves as a signpost towards the incomplete, prompting us to consider what new structures might stabilize the foundation. That is why many consider the Higgs more than just a solved mystery. It connects the most minor scales explored in colliders to questions about cosmic longevity. It reminds us that physics need not conclude with completeness. It can reveal the limits of current explanations and suggest what might lie beyond. And this naturally leads us to look ahead. While the Higgs has solidified the Standard Model, it has also raised new questions. Far from marking the end of a journey, its discovery signals the start of a broader exploration. Beyond the Higgs boson itself lies a greater mystery. What deeper structures might exist behind the Standard Model? The 2012 discovery was crucial, but it also left physicists with a clear sense that the story is not finished. The boson is confirmed, yet many theories suggest it may not be the only one of its kind. The Standard Model predicts a single Higgs boson, one scalar particle with a well-defined set of couplings. It is sparse, consistent, and even elegant. But in its minimalism, it might also be incomplete. Many extensions of the model view a lone Higgs as unlikely. Instead, they propose additional scalar particles, new symmetries, or even more complex structures underlying what we observe. The 2 Higgs doublet model, for instance, proposes not just one, but 2 Higgs fields. In such a scenario, the particle confirmed at 125 giga-electron-volts would be just one member of a family of 5. 2 charged bosons, 2 neutral scalars, and 1 pseudoscalar. They would vary in mass and properties, playing distinct roles in the balance of forces. Supersymmetry, in its minimal form called the MSSM, makes a similar assertion. It posits that every known particle has a heavier partner, a shadow that balances the equations. Within that framework, the Higgs cannot exist alone. There must be at least 5, with the discovered boson being only the lightest and most accessible. Other speculations go even further. Some propose that the Higgs is not an elementary point-like particle at all, but a composite made up of more fundamental parts held together. In that view, the boson we observed is less like a building block and more like a molecule, stable only because of deeper interactions among hidden constituents. Much like protons, long thought indivisible, were found to contain quarks. The Higgs could reveal itself as a hint towards another unseen layer. What unites these ideas is a shared feeling of unease with simplicity. Why should nature use a single scalar field to generate mass? Why does the Higgs potential take its particular shape? The discovery confirmed the mass-generating mechanism, but didn't explain its deeper origin. Instead of providing closure, many physicists see arbitrariness. A lone scalar particle, appearing neat and solitary, seems suspiciously minimal, more likely a fragment of something larger, visible only through today's advanced machines. That is why the focus now is on precision measurements. The Higgs boson discovered at the LHC can be examined in detail. How frequently does it decay into pairs of photons, bottom quarks, or W and Z bosons? Does it interact with matter particles like muons exactly as theory predicts? Each of these channels is carefully scrutinized because even tiny deviations from expectations could be the first signs of new physics. The boson is no longer just a confirmation of the Standard Model. It has become a tool to test its limits. One crucial parameter is the Higgs interaction with itself, known as the self-coupling. In the Standard Model, this quantity determines the shape of the Higgs potential and underpins vacuum stability. However, it remains unmeasured. The main way to test it is through Higgs pair production, events in which 2 Higgs bosons are produced simultaneously in a collision. These are extremely rare, yet they provide a direct window into the field's most fundamental property. Future colliders will prioritize this measurement as a key goal. Alongside such measurements, connections with broader mysteries persist as speculation. Dark matter, which makes up most of the mass in galaxies, remains undetectable through direct observation. Some theories suggest the Higgs might weakly interact with dark matter particles, offering a faint but testable link between known physics and the unseen majority of matter. In early universe cosmology, the energy surge known as inflation still seeks its explanation. Some propose that Higgs-like fields could have helped initiate, or at least interacted with, that rapid expansion. Even the ongoing accelerated expansion of space, often attributed to dark energy, has led some theorists to wonder if scalar fields related to the Higgs could be involved. These are not certainties, but possibilities, open doors that data might eventually help narrow. That speculative horizon explains why the Higgs is now seen as a magnifying glass. Instead of merely asking whether it exists, researchers scrutinize it relentlessly. They use it to examine the standard model's fine details. The boson becomes a benchmark. Measure it, verify it, confirm it against quantum predictions calculated through multiple loops of complexity. When every measurement so far matches expectations within error margins, it boosts confidence. But if a single discrepancy appears, one decay rate that deviates, or one coupling that proves weaker or stronger than theory expects, that becomes the opening to deeper physics. This marks a shift in perspective. Initially, the Higgs felt like an exclamation mark. The final piece needed to complete what was already a near-perfect model. But viewed today, it seems more like a keyhole. Look through it, and you might see the outline of further structures beyond. New interactions, new families of particles, an explanation for why something as widespread as mass appears in this particular form and not another. This is why large-scale projects now focus on the Higgs as their core target. Whether in the form of a new linear collider or an even larger circular one, future accelerators are planned not just to discover, but to produce Higgs bosons in unprecedented numbers. The goal is to turn invisible differences into visible ones, collecting enough events that even a 1% deviation in some decay rate cannot be hidden. If those deviations appear, they will transform physics. If they do not, then the absence also speaks volumes, confirming the standard model with greater authority and narrowing the avenues for alternative ideas. That double outcome means the Higgs will guide the next chapter, regardless of the result. Discover a deviation and new physics emerges. Find none, and the limits of the standard model extend further than imagined. Either way, it is the particle that determines where focus must shift. Its behavior has become the compass pointing towards the field's future. You can see why the Higgs is not merely an answer but a threshold. It provides us with a particle confirmed in detail, yet also leaves a lingering sense of incompleteness. Each new measurement not only boosts confidence, but also sharpens the search for areas for improvement. Each increase in precision tells us either that nature's laws are more restrictive than expected, or that surprises lie in the fine print. And so, even as laboratories process complex datasets and design new detectors, the Higgs holds a meaning that is more than just technical. Its discovery demonstrates what particle physics can achieve, but its role now extends beyond equations. The boson itself is an anchor for science, yet also a reminder that knowledge is always provisional, remaining open for questions yet to be asked. At this stage, a different kind of reflection arises, one less about technical details and more about what the Higgs has come to symbolize. What the Higgs ultimately came to represent was more than just a breakthrough in physics. It was a profound shift in our understanding of the universe. It became a symbol of perseverance. For physicists, the boson was the final missing piece that completed the standard model. But the broader story is about how humanity faces the unknown. For decades, researchers worked with only equations on paper and probabilities on graphs, convinced that a hidden field must exist, even though they could neither touch nor see it. They followed only the faintest trace, a ghost implied by mathematics, supported by the hope that patience and reason would eventually uncover the truth. To many outside the research sphere, that quest appeared unusual, even lavish. Why spend such extraordinary sums, mobilize thousands of scientists and engineers, and dedicate entire careers to something so abstract? Colliders cost billions to construct, and their purpose was not to produce a new material or medical breakthrough, but to verify the existence of a hidden particle. The question was valid. Why should humanity invest resources in such a distant issue, one whose resolution would not immediately feed a family or cure a patient? The contrast with other scientific fields sharpened the skepticism. Advances in electronics quickly led to the development of faster phones and computers. Progress in medicine delivers new drugs and longer lives. In these fields, a clear link exists between discovery and the benefits it yields. With the Higgs, such a connection was not obvious, demonstrating that mass arises from interaction with an invisible field, doesn't warm homes or grow crops. It merely reveals how nature functions. For many, the benefit seemed intangible, and yet, over time, the Higgs came to represent something profound. Its pursuit exemplified the value of knowledge for its own sake. It implied that trying to understand reality, even when no profit or immediate benefit follows, is part of what it means to be human. That shift gradually transformed the Higgs into a cultural symbol. It was no longer merely a hidden component of the standard model, but a signal that curiosity, even in its most abstract form, deserves effort. The story also demonstrated extraordinary patience. The mechanism explaining the Higgs was written down in 1964, but confirmation did not arrive until nearly 50 years later. During that long period, careers began and ended with no direct sight of the boson. Technologies that promised proof were discussed, delayed, canceled, redesigned, and eventually built. Yet the community persisted, carrying the idea across generations. Few pursuits show endurance on that scale. It is one thing to chase technology promising wealth or competition. It is another to pursue a particle invisible to all instruments, trusting that evidence might one day be found. An image comes to mind, planting a seed that may or may not flower. You water it, knowing you might never see it bloom, yet others continue to care for it when you cannot. In the case of the Higgs, the flower did appear. The blossom was the discovered particle itself, and the fruit, the clarity it brought to our understanding of mass. The patience that kept the seed alive turned out not to be wasted, but vindicated. The discovery proved that waiting for invisible truths can yield more than faith. It can produce reality. Alongside persistence stood a form of intellectual trust. The Higgs boson was not discovered through a fortunate measurement, but was predicted years earlier, supported solely by reasoning about symmetry and consistency. Theorists argued that if nature were coherent, then the Higgs must exist. Even without definitive proof, they resisted abandoning the idea. That commitment was a quiet act of courage, a statement that principles of logic deserved decades of effort in laboratories and entire industries built around them. When the boson finally appeared, it was not by chance, but a reward for faith in ideas. Global cooperation was equally essential. The Higgs boson was not discovered by one institute or one nation, but by a collaboration spanning the world. Thousands built the Large Hadron Collider together, uniting skills and knowledge across borders. That effort became a shining example of how humanity can band together in pursuit of a question with no immediate reward other than understanding. In a century often marked by conflict and division, the Higgs stood out as something different, a triumph not only of science, but of collaboration. That same cooperation had practical consequences. Searching for the Higgs involved handling enormous volumes of data that were more than any single site could process. The solution was the worldwide LHC computing grid, a network of facilities across many countries working together to sift through petabytes of data for signs of new physics. This infrastructure advanced techniques in distributed computing and data management. But beyond these benefits, the true legacy was proof that humans could create a tool of planetary scale simply to pursue a hidden truth. When you step back, that is what the Higgs represents in culture today. It demonstrates that unseen mechanisms underpin reality and that disciplined thought can reveal them. It confirms that knowledge itself can be pursued, even when practical outcomes are distant or uncertain. It also shows that human perseverance can span generations, uniting people in a long arc of discovery. So if you are tempted to question the value of abstract science, remember the Higgs story. The pursuit yielded advances in engineering, magnet technology, and global computing. But even if it had not, the discovery that mass arises from a hidden field remains a triumph. It proved that ideas from blackboards could one day make invisible structures evident through nothing but persistence, logic, and unity. There is humility in that. The Higgs boson itself is tiny and unstable, vanishing before it can blink. Yet its significance is immense. It teaches that patience matters, that borders need not limit cooperation, and that seeking to understand reality is a valid human pursuit, as is any material improvement. Every move you make, every object you lift, is only possible because of the Higgs field. However, the effort to confirm it stands as proof that humanity can reach for truths that at first seem unreachable. For us, the Higgs is living proof that the unseen can be revealed indirectly if you think carefully and build boldly. It shows that abstraction can become confirmation, and ideas can drive the construction of machines the size of cities to detect particles that survive for less than the blink of an eyelash. In that sense, it brings permanence to what was once speculation. It demonstrates that reality, though hidden, can be brought within reach through persistence and perseverance. This is why the Higgs resonates beyond physics. It tells us progress is not always about immediate rewards. Sometimes it is about asking questions that seem impossible and refusing to give up. Between 1964 and 2012, the Higgs was an idea waiting for evidence. Its discovery was not just a scientific triumph, but a story of human resilience in the face of uncertainty. And at the end of this long quest lies something greater. The Higgs does not merely complete an equation. It reflects how unseen forces can shape everything we experience and how persistence allows us to uncover them. This understanding serves as a bridge to more profound thought about what mass truly is and how to perceive it in the world around us. Mass is not carried as baggage, but arises from the physics of particles themselves. For elementary particles like quarks, electrons, and the W and Z bosons, mass results from how strongly they interact with the Higgs field and its non-zero background value. Most of the mass of protons and neutrons, however, comes from the binding energy of quarks and gluons within the strong nuclear force. Together, these two sources explain the weight of everyday matter. The solidity of a chair or the structure of your body depends on atoms, chemistry, and the tiny electron masses provided by the Higgs. Without those, electromagnetic bonds could not maintain form. The more profound lesson is that unseen features of reality, such as the Higgs field's constant background, quietly shape the world of experience. You may never observe such a field directly, yet its presence makes stars, planets, and life possible.